This is lecture number 3 from the chapter 2 Variable Regression Model, the problem of estimation. In this lecture, we will discuss numerical properties of OLS estimators. Properties of estimators are classified into two categories. One is numerical properties and the other one is statistical property. Numerical properties are those that hold as a consequence of the use of ordinary least squares, regardless of how the data were generated. And on the other hand side, statistical properties are those that hold only under certain assumptions about the way the data were generated. We will discuss the statistical properties in upcoming lectures and confining our today's lecture to the numerical properties of least squares estimators. So the property number 1 is the OLS estimators are expressed solely in terms of the observables, that is sample quantities x and y, therefore they can be easily computed. You know that beta 1 hat is equals to summation xi minus x bar yi minus y bar over summation xi minus x bar square. And if we have the data of x and y, we can easily compute the value of beta 1 hat. Similarly, beta naught hat is equals to y bar minus beta 1 hat x bar, and if we determine the values of beta 1 hat and also the values of x and y, we can easily compute the value of beta naught hat. So OLS estimators are expressed solely in terms of sample quantities, that is x and y, therefore they can be easily computed. The second numerical property is they are point estimators. That is, given the sample, each estimator will provide only a single, that is point value of the relevant population parameter. It means that once we have a set of xi, yi, we will obtain only a single estimate for beta 1 hat and beta 2 hat. Unlike interval estimator, in case of interval estimators, instead of providing a single estimate to the parameter, we suggest a range within which parameter will lie. What is our population regression line? It is E of y conditional xi is equals to beta 1 hat plus beta 2 hat xi. We estimate this by using yi hat is equals to beta 1 hat plus beta 2 xi. I have taken the non-stochastic form here. Here beta 1 hat is the estimator of beta 1 and beta 2 hat is the estimator of beta 2. Now suppose that beta 1 hat is equals to 11.9. So this is one single number and this is the point estimator. Similarly, for beta 2 hat, it is equals to minus 0.65. So again, it is a single number. That is why they are known as point estimators. But in case of interval estimation, we suggest a range. For example, estimate of beta 2 hat lies between 0.4 and 0.8. So the estimate of beta 2 hat lies between 0.4 and 0.8. And the estimate of beta 1 hat lies between 30 and 60. And we will study interval estimators in detail in our next chapter. Now the third property is, once the OLS estimates are obtained from the sample data, the sample regression line can be easily obtained. Now the sample regression line is given as yi hat is equals to beta 1 hat plus beta 2 hat xi. Once beta 1 hat and beta 2 hat are obtained by adding the values of xi, we can determine yi hat. And plotting these values, we will get the sample regression line as an estimator of sample regression line. The sample regression line so obtained passes through the mean values of x and y because, as we stated earlier, we know that beta 1 hat is equals to y bar minus beta 2 hat x bar. So that y bar is equals to beta 1 hat plus beta 2 hat x bar. In the form of graph, this is the regression line, that is equals to yi hat is equals to beta 1 hat plus beta 2 hat xi. This point is x bar. Suppose that this is x bar. One point on sample regression line will be intersection point between x bar and y bar. So sample regression line passes through the mean values of x bar and y bar, and y bar is equals to beta 1 hat plus beta 2 hat x bar. So this distance, this one, is equals to beta 1 hat plus beta 2 hat x bar, and this is simply the x bar. This is all from the third property. Now, fourth property is the mean value of the estimated yi, that is yi hat, is equal to the mean value of actual y. What we are trying to prove is the mean of the estimated y is equals to the mean value of actual y, that is yi bar. So we are trying to prove that yi hat bar is equals to yi hat. We have, let's suppose that we have data on x and y, and suppose we run a regression and get the equation that yi hat is equals to 11.9 minus 0.65 xi. If you calculate the mean values of y and calculate the mean value of yi hat, so this property says that you get the same answer, that you get the same answer. Let's prove this. We know that yi hat is equals to beta 1 hat plus beta 2 hat xi, and here beta 1 can be written as beta 1 hat can be written as y bar minus beta 2 hat x bar plus beta 2 hat xi. If we take beta 2 common, so we get here yi hat is equals to y bar plus beta 2 hat, as we take it common, xi minus x bar. So summing both sides we get summation yi hat is equals to, now sum of y bar is n times y plus beta 2 hat summation xi minus x bar. So it means that summing both sides does not change the equation. So summation yi hat is equals to ny bar plus beta 2 hat summation xi minus n beta 2 hat x bar. Now beta 2 here is constant and x bar is also constant, so we get n beta 2 hat x bar. Now dividing both sides by n, we get summation yi hat over n is equals to ny bar divided by n plus beta 2 hat summation xi over n minus n beta 2 hat x bar over n. Here n cancelled out, here also n cancelled out with n, so we are left with summation yi hat over n is equals to y bar, as n is cancelled out here, plus beta 2 hat summation xi by n minus beta 2 hat x bar. Here again n cancelled with n, so beta 2 hat x bar is left here. So now here, what is summation xi by n? Summation yi by n. This means that you are taking average of estimated value. So this is yi hat bar is equals to y bar plus beta 2 x bar minus beta 2 hat x bar. Here x bar comes as a result of this one, summation xi by n. So summation xi by n is equals to x bar. So beta 2 hat x bar minus beta 2 hat x bar. So these two terms cancels out and we are left with yi hat bar is equals to y bar. So this term actually, summation yi hat over n is equals to yi hat bar. So yi hat bar is equals to y bar. This means that this whole term means that the mean of estimated value is equal to the mean of actual y value. Hence, this property is also proved here.